Hi everyone. This is Sai from Let's Upgrade. So let's talk about how to get your certificate. It's very simple. You will see two links in the description. Number one is the place where you have to go and mark your attendance. Marking your attendance tells us like, okay, you are a legit student who have attended this particular session. Link number two is your assignment. This is where your 90% of the priority is. You have to go and submit the assignment that is given to you in this particular session. Once you're done submitting that assignment, we will be evaluating that. We will send you an email. If you get the passing criteria, then only we will give you the certificate on a particular date that is mentioned again in the description. Please check these three things, and this is the way how you will get a certificate from Let's Upgrade. Number one, mark your attendance. Number two, just go ahead and upload your assignment. Check for the email that you have received it, yes or no. What is the feedback that you have received from your trainer? Number three, check on which date the certificates will be released. Thank you. Bye. All the best. Happy learning.
Hi there, welcome to another interesting workshop. The name of this workshop is Introduction to Scikit-learn Classification, right? So, as the name implies, what we're going to do in this workshop is build a classification model, classification machine learning model using the Python library Scikit-learn. So, let's have a look at the contents as to what all we're going to do here. So, we're going to be having an introduction and overview, which is the current part of the session, and then we're going to discuss the software and requirements for the workshop. Then we're going to download the dataset, post which we explore the dataset and then understand the dataset more. And then we have these coding exercises, right, where we have the input data and exploratory data analysis, and then we pre-process and then implement the model, and then we do the final model analysis, right? So before performing all these steps, it's necessary to understand like what we are exactly going to do here. So classification is basically, if you look here, it's an algorithm that sorts data into distinct categories or classes, right? So given the fact that you have, say, a group of apples and a group of oranges in the input data set, then what the machine learning model does is it learns patterns from that data set. And then if you feed that with unseen data, it tries to predict the category for that unseen data, whether it's an apple or an orange, right? Similarly, for animal classification like dogs or cats, it does the same thing. So, what we are basically going to do in this workshop is we're going to be trying this model on a finance data set, right? So, typically in the real world, problems go like this, that you have a large data set of input features and output value, and the output value looks like whether, say, a person has defaulted on the loan or not defaulted on the loan, right, as a function of various parameters like the loan tenure, the payment amount, the number of years in his job. So based on these parameters, the person basically learns to figure out whether the loan is a default or not, right? So that's what you're going to do in this class. So let's try that out in the subsequent sessions. So now let's discuss the next part, that is the software and requirements. So as you see here, what we're going to require is basically a version of Python on your machine, which is 3.10 or higher, because we are going to implement this classification model in the Scikit-learn Python library, right? So the next libraries that we require are matplotlib and seaborn. So please make sure that before you work on this workshop, you download these three packages on your machine using pip install, right? So pip install sklearn, pip install matplotlib, and then pip install seaborn. Uh, Post you do that, you will be in a position to uh, perform the tasks, the coding tasks in this workshop, right? So um, because sklearn and seaborn, they both and in fact even matplotlib, I think they all of them um, comfortably work on a version of Python which is 3.10 or higher. So please make sure that you have these three versions, and then you'll be in a position to work on this workshop. So let's get started. All right. So the next step, in fact, the first step in this workshop is to download the dataset, right? So all machine learning algorithms are trained on some data, right? Some input data. And to get some sample input data, the best site is this kaggle.com, where if you go to kaggle.com/datasets, obviously you have to sign in with your credentials. If you do not have credentials, please create one. And once you sign in with your credentials, you're going to go to datasets by clicking on this and then search for the credit default dataset. right? Or maybe just go to datasets here and then search datasets, credit default dataset. And then if you click on this default of credit cards clients dataset, you see you get a sample dataset here, which you can download by clicking on this link and then go to that place where you want to save this. Right, so say save. Here you go, you have downloaded this. So just right click on this and then say extract here. So here you go, that's it. So we have downloaded the dataset. So now in the next section, let's explore this dataset and then see what all columns we have in this dataset, right? So that will give us a glimpse of what we have to infer in the actual machine learning model. So without wasting further time, let's delve into the actual dataset. Here we go. All right, so here's the extracted file from our directory, which is named as UCI underscore credit underscore card dot CSV, right? So we just downloaded this data from Kaggle. So this is a credit default data set where if you interpret this in this way, it basically means that it has these 25 columns, and the 25th column is actually that column which gives you an insight of what has actually happened to this client in that particular for that particular client, right? So for a particular client with say a limit balance of 20,000, gender, education, marriage, age, six payments, we will see in detail all what all of these parameters mean. But then basically at a high level, what this basically tries to infer is that as a function of these 24 parameters, this had been the default category for this client. So a default of 1 means an actual default, and a default of 0 means no default, right? So if the 24 parameters looked in this way, then this client defaulted in the next month. If the 24 parameters looked in this way, then the client did not default for that particular in the next month, right? For these set of parameters, right? So the motive of this model is to basically study these number of rows. So how many rows do we have? We have 30,000 rows, right? So we have 30,000 historical records along with their associated values of default, whether it's 1 or 0. So what this model is going to do is it's going to basically study these 30,000 instances and then infer from these instances and then devise an algorithm. Basically, I mean, we would be choosing the algorithm ourselves, but an algorithm would learn from these 30,000 instances and these 24 parameters. And then the idea here is if you feed the algorithm with unseen data, right, then the algorithm should be able to correctly predict whether the default is a 0 or a 1, right, for the next month. So what we are going to do is we're going to divide the same data of 30,000 rows into a training data and testing data, right? So some of these rows are going to be training data. Let's say maybe 70% of the rows are going to be a training data set, and the remaining 30% are going to be testing data set, right? So once we train the model on these 70,000 rows, I mean, let's say for example, then the idea is to feed those 30,000 rows and then allow the model to predict the values of column Y of the default column for those 30,000 rows, and then cross-validate whether the predictions made by the model matched with the actuals, right? And how many cases the predictions matched with the actuals. So we shall see the detailed analysis later in this section, but that's basically the idea, right? So to have a clue of what each of these columns means, I mean, let's look at it at a high level. So ID is basically the ID of each client. I mean, that's only a serial numerical number. Limit balance is the amount given in credit in dollars, right? Basically. Then this is obviously the gender. So one means a male and two means a female. Education. So like these stand for different educational hierarchies, right? So like one means graduate school, two means university, three means high school, so on and so forth. It has its own table here if you want to go into that detail right now. Marriage, yes, I think one means married and two means single, three means others, I mean something else. Then age is age in years. Now these pay 0 to pay 6, these are basically the repayment statuses. So pay 0 is a repayment status in September 2005. Pay 2 is the repayment status in August 2005. And pay 3, pay 4, pay 6, right? This is about the previous months, right? So similarly, bill amount one is the amount of bill in September 2005. Bill amount two is the amount of bill in August. All right. So the first thing that you're going to do is open a Jupyter notebook like this, as you see in the window. So make sure that you open the Jupyter notebook from the same location where the dataset has been saved, right? Otherwise, we would have to give the absolute path in the code, which we do not want to do to avoid verbosity of the code. So just make sure you open a Jupyter notebook, a new notebook in the same location that we have saved the input dataset. So the first thing we do is import the libraries. So this section basically deals with the data input and the exploratory data analysis, right? So let's do it step by step. So let's say import the necessary libraries, and then let me add all the libraries that are required right here. Now let's run this piece. Guess there should be no issue running this one. And then, so this is for something which you want to do later. Like if we want to set up the visualization style for your seaborn and your pandas and your matplotlib, right? So we just do it right away so that we don't have to do it later. This is just to set up certain standards for your data visualization. And then now the next thing that you do is now you're going to be loading and preparing the dataset So the file name you give is dataset file name. Then let's say we add a try block. So you read the file. Then we are renaming certain columns, like the last column, right? Default.payment.next.month. We are renaming that to default, right? And pay zero, we are renaming that to pay one, just to keep consistency, right? And then we're also dropping the ID column because that's not required actually in the analysis, right? That ID is just a serial number that does not impact the model building in any way, correct? So we're dropping that column. Then we have an exception here. If things don't work out, then we need to add an exception, right? Let's run this one. Okay, so it's successfully run here. So if so, once the asterisk mark goes away, right, that shows that Jupyter has successfully finished running the cell. It's the case here. So now let's do something. Let's drop. Let's split this data into X and Y. So like X is going to be all the input features, and Y is going to be the output column. That's default, right? Which we are trying to predict. So let's divide this into these two types in this cell, which we have done here. Then next thing we do is we split the input features into numerical and categorical, right? So numerical are the ones which are basically amount values, or like say age, education, and categorical ones. I'm sorry. Numerical ones are like the payment values, right? The ones which have like say continuous dollar values, not like discrete categories like zeros or ones. They are basically those numerical features. And categorical features are the ones which have discrete values like 1, 2, 3, like age and gender, education, right? Marriage status. So let's define them. Um, right. So these are all the categorical features, and then numerical features are the ones all apart from the categorical features. So from the x dot columns, you drop all the categorical features, and then you get the numerical features, right? Right. Now let's do the now. In this way, we have actually read the input data successfully, right? We have uploaded the data, and then we have split the data into features and the output. Now the next part is to explore the data. So now we need to understand the data further, right? In order to do that, we need to do some exploratory data analysis. So let's do that now. Uh, let's add a header here. It says like we are doing the EDA, just like a divider. So now what you're going to do is two things here, like the data types of each of the columns, and then identify the data types of each of the columns. And the second thing is you're going to do missing value imputation, right? Let's do the first part. So you see all the 24 columns, right? Some of them are float, and then some of them are int. I think the categorical are all integers, and the numerical ones, the payment amounts, all of them are basically floats, right? So this pay one, pay two, pay three, that's basically also a categorical column. It's not a it's not a numerical column. So just keep that in mind. It stands for what? It stands for the amount of previous payment in September. So like these are categories, right? And then now what you're going to do is you're going to do a missing value imputation. So what is missing value imputation? If the dataset contains any missing values at any point, right? Our job is to attend those missing values, maybe delete those cells which have missing values, or maybe replace those missing values with some legitimate value, so that it basically makes the data set consistent, right? Because if the model encounters any missing value, it might produce erroneous results, or it might not produce some results at all, right? It might encounter errors while producing results. So that's why it's necessary to address these missing values. Sometimes what we do is we replace those missing values with the mean value of the entire column, or the median value of the entire column, depending upon the situation. So that's called as missing values imputation. That procedure is called as missing values imputation. So that's exactly what we're doing right now. The next step, that is missing values imputation. So we say the missing values are basically data frame dot is null dot sum. I hope you all are familiar with the pandas data frame. So if missing values dot sum is greater than 0, then what you do is we address those missing values, right? So Scikit-learn gives you a tool called as a simple imputer, right? That's meant to impute the missing values. So it automatically addresses the missing values therein. And then it says, when you say imputers.fit transform, it basically uh, transforms the data set. In this case, it's only numerical features, right? It transforms this into a data set where all the missing values have been addressed and imputed, right? That's what we do. And else print no missing values found in data set. So let's see. Okay, so fortunately, no missing values have been found in the data set. So we are safe, we are good to go, right? Now the next step is, what we do is we try to find out the imbalance in the class. So what is imbalance in the class? This class refers to exclusively the output class, right? The default column. So how many zeros do we have? How many ones do we have? So if we have zeros and ones in more or less the same proportion, that means the class is balanced. However, we have, if one of these classes extremely large compared to the other classes, right? That means there's a class imbalance, and we need to handle this class imbalance later while developing the algorithm. Otherwise, we run the risk of our algorithm producing erroneous results, right? So let's first check out what the class imbalance is. So this is the y value counts. Then we check the ratios, and then we are printing the total counts here. So let's see. So you see the number of zeros, that is the number of non-defaults, are 23,364, and the number of defaults are 6636, right? So this data is highly imbalanced with, like, say, 22% of defaults within the 30,000 rows. So we need to handle this imbalance later. So it's definitely not a balanced data set. However, while actually running the model, right, we are going to be using the balanced, we are going to assume a balanced data set before, and then we are going to compare those values with the ones which we observe when we use an imbalanced data set. All right. Let's do both the analysis and then see how things work. All right. So we are good to go with this. The next thing that we do in is basically do in this section is basically an exploratory data analysis. So let's do that. So what we do is we basically we're plotting the values here. Uh, I mean the section that we observed above, right? This one, the default. We first plot a graph showing the distribution. So as you see here, this is 23,000 odd values, and these are like 6,000 odd values, right? So that's the distribution here. And then the next thing we do is, now in the next section, what we're going to do is we're going to try to see the outliers for the individual features, right? And for this outlier analysis, the best analytical method is a box plot. So let's do the box plot here for the numerical features. Again, not for the categorical features. So what we're going to do is for each of the numerical features, right? We're going to plot a box plot. Right, so here we go. This is the box plot for each of the numerical features. So as you see, limit, balance. So what a box plot tells you is basically the quartiles, right? The first quartile, second quartile, third and fourth quartile, the inner quartile range where it lies. This is the inner quartile range. This is the these are the outliers, right? So these are the outliers, the for the top end and the bottom end. So for each of these columns, like the limit, balance, age, bill amount 1, 2, 3, 4, 5, 6, then pay amount 1, 2, 3, 4, 5, 6. For each of these amounts, right? We have a box plot. So you see there are many outliers here. However, we do not worry about them at this moment. We still proceed with the analysis. This is just for our understanding, right? It's not that the outliers are always a concern, but it's just to give you a high level overview of how the data is basically scattered, right? That's why I use a box plot. The next tool that we use in exploratory data analysis is a heat map, right? Because we want to see how correlated are the different input features with respect to each other. In this case, we are doing an analysis between only the numerical features, right? Because we can do a different a chi-square analysis for the categorical features, which you're not going to do here. We're just doing it for the numerical features. So let's do that. Say correlation matrix. And we plot a heat map. And then we can give a title to that. Let me show that, right? So here you go, that's a heat map. So let me just reduce the size of this for your visualization. So as you see here, right, uh, in this heat map, you have different colors. So the red colors are basically the ones, the cells, which have a high correlation with each other, right? And then the light colored ones are those cells which have a lower correlation. So the lighter the color, you see 0.3, 0.29, 0.31. These are the lightest colors. So they have the least correlation with each other. So you see, like pay amount 3 and then bill amount 4, they have the lightest colors, so they have the least correlation. And say bill amount 5 and then bill amount 4, they have a high correlation, so they have 0.94 as a correlation value with a dark red color, right? So if you look at this chart, this basically shows the variation in correlation. This is the scale. So it all begins here. So a dark blue is the lowest correlation, and as it increases here, right, as the blue gets lighter, the correlation increases, and then it becomes greater and greater until it becomes red. So orange is an intermediate correlation, and then red becomes darker and darker until the correlation becomes the highest, right? So that's basically what the heat map tells you. Okay, let's expand this once again, right? And then now finally we have another section, the final section in this exploratory data analysis, where we basically talk about the histograms, right? So these histograms basically show the class distribution against every feature. So uh, the actual code will make it clear. First, we plot the histogram for the numerical features. And let's run this. Let's wait until it runs. Right, so here we go. So how do you interpret this? So all the values for limit balance, right, between a particular range, like from 0 to 0.2, 0.4, zero point 0.6, you have been given a count of the class zeros as well as class ones for each of these values, right? That's basically how we interpret this plot. Like if you look at age 20, you have these many uh, yeses and these many no's, right? So the green means a yes and the blue means a no. So for age 20, between age 20 to 30, you have these many yeses, these many no's. So the blue ones are the no's and the green ones are the yeses. That's how you interpret this, right? Similarly, let's do the analysis for the categorical features. Right, let's run this. All right, here we go. So if you look at this, the default rate, right, by gender. So the default rate of one, and I mean, a gender of one has this default rate, and a gender of two has this default rate, right? Uh, then education. So education's categories of 0, 1, 2, 3, 4, 5, 6. They all have these default rates basically. Clear? I think that's how you interpret this. All right. So if you look at default rate, that basically is, you've done it before, right? Here, right? It's df.group by feature default dot mean dot sort dot index, right? That's basically the metric which you're using here. All right. So with this, we have successfully finished the exploratory data analysis. We have fed the input data, and then we have analyzed the data very well to understand how the data is dispersed basically and distributed. So now in the next section, let's build the actual model, and let's pre-process the data first for feeding the model, and then let's build the actual model, right? So without wasting further time, let's get into the next section of building the model. Thank you. All right, so in this section, what we will be doing is first pre-processing the data required to be fed to the model and then run the actual model, right? So let's write this part as pre-processing and model implementation. And let's have a placeholder to run the model. So the model that you're going to choose here is logistic regression. The reason being, it's the best models to start with when it comes to uh, inferring from a binary classification data set, right? So this is a binary classification problem. Why? Because you have just two values in the output, a 0 and a 1, right? If you would have many values, many more values, then logistic is not that great. But then if it's a binary classification problem, the first model that you use up front is basically logistic regression. And the other advantage of logistic regression is that it really helps you understand the contribution of every feature in the final output analysis of the model, right? So because of these two reasons, we're going to choose logistic regression. Then we split the data. Okay, so let's see, this is done. Now we split the data into training and testing sets. So there's a class called as train test split, using which we right. So now the next thing we do is manual pre-processing, right? So one of the important aspects of pre-processing is this one hot encoding. So what is one hot encoding? The categorical features, right, like which are fit into categories like 1, 2, and 3, they need to be split into respective columns. Like say for example, if you have two values in gender, like gender equals 1 and gender equals 2, like 1 is male and 2 is female. So instead of having the same column having ones and twos in different rows, what you do is you have one column for gender 1 and the other column for gender 2. So wherever a gender 1 value is present, it's going to be adding a 1 over there and 0 everywhere else. And in the gender 2 column, wherever the gender 2 is present, in those rows, it's going to be adding a 1 and 0 everywhere else, right? That's basically one hot encoding. So that's what we're doing here. This enables the model to better interpret the input data. That's why we do this. right? And then, give me a second. Thereafter, we realign columns. That's important for consistent feature sets. So that's how we have encoded the training and testing, right? Both training and testing. So as you see here, 30% of the data is going to be a testing data, and then 70% is training data. And then what is this random state is equal to 42. Like 42 is any random number, but then what we're ensuring is that since we have specified some number over here, the next time you run this notebook, it's going to look at the same number here, and then the same random rows which are selected for training and testing, they're going to be retained in the next iteration as well. So like this, you ensure that suppose like row numbers 2, 3, 7 were the testing rows in your iteration 1, the same rows remain as testing rows in the iteration 2 as well. That's what you ensure using this random state. If you do not specify random state, then it's going to select some other rows as the rows for testing, right, in the next iteration. So just be worried about that. And then we identify numerical columns for scaling, right? Now, what we're going to do is we are going to do a feature scaling. So why do we do this? Because like some columns have a magnitude in say thousands, right? Some columns have a magnitude in say tens. Some columns have a magnitude in decimal numbers. So to make them comparable, in order to ensure that the model does not prioritize the high magnitude columns over the low magnitude columns, what we do is we scale those columns. So what the scaler is going to do is that it's going to scale those columns to a comparable magnitude so that the model gets a better assessment of the input data set. So all right, so we have encoded the models now, encoded and scaled them as well, right? And then the final part is to, so we run this component first. So the pre-processing is complete. And then the next part is to initialize and train the model, right? So we do that now. So we're using logistic regression. So see, we are custom weights here. We'll explain the meaning of this parameter later. At this moment, let's say we're using class weights as balanced, right? Right now we aren't using this parameter, so just ignore this. Right, so there's the model, and then what we do is we use this model dot fit to fit the model on this data. So this model has successfully been trained now, and then the final part is to make predictions and evaluate, right? So the way we do it is we say y predict as model.predict. So what we're doing here is this model, which has been trained on this training data set, we are feeding it with the testing data, the input features for the testing data in the form of X test encoded. And then this basically gives you the y predicted, right? These are the predicted values. Now what you're going to do is you're going to use this y predicted to assess the accuracy and the fitment of the model, right, in the next section. So with this, we are done with uh, the model pre-processing and then the model fitment. So in the next section, let's actually evaluate how accurate the model is, right? So without wasting further time, let's delve into the next section and let. All right, so now we are into the final component of the code where we do the evaluation of the model. So let's write this as final model analysis, then add a placeholder to print the final model analysis. Right, so the first thing is a confusion matrix. So what is a confusion matrix? Let me actually plot that, it will make it clear. So let's print the confusion matrix and then let's talk about that. So here you go, we have finished running this piece of code and plotted the confusion matrix. So you see, the confusion matrix is a plot of the actuals versus the predicteds, right? So you see the actual default zeros in the testing data set were like, it's going to be something like 5853 plus 1156, right? Out of which 5853 were predicted to be uh, default by the model, and then 1156 were actually belonging to this class 0, but then they're predicted to be class 1 by the model. So this is an error in the model, right? But then our job is to design such a model that reduces the amount of errors. So lesser the values of ones for the actual zeros, better, right? And then similarly for the class 1, out of the values which belong to class 1, 1123 values were correctly predicted to be belonging to 1, and then 868 were incorrectly predicted to be belonging to 0, right? So they actually belong to class 1, but then they were they were predicted by the model as to be belonging to 0. So we have to reduce this number and this number, and we have to retain this number, and we have to increase this number and this number, right? That's the motive of a confusion matrix, right? So one point to understand here is that we are not that much of concerned about how many of the predicted non-defaults get categorized as actual defaults, because we are more conservative when we create these default models, right? We are more worried about retaining the actual defaults. So the concern here is that if those rows which are classified as defaults, if they incorrectly get classified as non-defaults, then that's actually a mistake which is far more dangerous than this mistake, right? In fact, if the non-defaults get categorized as defaults, then actually we are fine, we are good to go. We are on the safer side. But if the defaults get classified as non-defaults, then we are not good to go, right? Then we are unsafe. So the main motive, so this analysis basically varies from case to case. So for this particular use case, right, of credit default, we are always concerned about the recall for the actual default. So the recall is basically the number of incorrect values upon the total values, right? So that number we need to increase. I mean, the recall is the number of correct values divided by the total values, right? So that number we have to increase for this class, actual default 1, in a correct default dataset. So let's keep that in mind, because later when we talk about the class imbalance, right, we're going to be balancing the class in such a way that the results produced for this category 1 are the most are the ones which have the highest recall, right? So that's just the background. And then the next thing that you do is the ROC curve, which is the receiver operating characteristic curve. What this curve does is it basically plots a graph of the true positive rate versus the false positive rate, right? So what is true positive and false positive? If you look at this category 0, then all the zeros classified as zeros are true positives, right? And then all the zeros classified as ones are false positives, right? And in if a class like if category 0 is positive, then category 1 is negative, automatically becomes negative. Positive and negative is more of a relative term over here. If category 1 is positive, then category 0 becomes negative, right? So all the ones classified as ones are true negatives, and all the ones classified as zeros are false negatives, right? So the ROC curve is a plot of the true positive rate and the false positive rate. Okay. Then we basically convert this to a matplotlib plot. We actually plot the ROC curve using matplotlib. You can observe how it's being done. All right, so now we plot this curve. Let's run this line. And yeah, there you go. So this is basically the plot between the true positive rate and the false positive rate, right? So as you see, the baseline is zero point 0.5, and then the area under the curve is basically an important characteristic of the ROC curve. So if the area under the curve is greater than zero point 0.5, that means your model is really, really good, right? It it does a great job of correctly classifying the positives as positives and the negatives as negatives. And if the area under the curve is less than zero point 0.5, that means the model does the reverse job. It's not a good model. I mean, you can still interpret that in a reverse way, but then it does a reverse job, right? It classifies the negatives as positives and positives as negatives. That's how you infer. And if the area under the curve is zero point 0.5, actually zero point 0.5, that means the model is not doing a great job at all, right? So that's the ROC curve. And then the next thing we want to do is we want to be checking how does every parameter contribute to the actual model, right? So here's the thing. We run this part, and then now you see that the contribution of these parameters, like say pay1 has a coefficient of 2, pay13 has a coefficient of 1.89. So these are in, like, say, descending order. So this parameter contributes the most towards the default, right? So higher coefficient means, like, if this parameter has a higher value, then there's a higher value of default, right? And if this has the lowest coefficient, right, the negative coefficient. So if this parameter is existing in the dataset, then it's contributing to not much to the likelihood of default, right? That's what you basically mean. And these are the classification reports. So you see the default, I mean, the recall for this parameter one is it's not that great. It's 0.56, whereas recall for 0 is 0.84. So we need to change these numbers, right? Let's do one thing. Let's have the custom weights here, and then let's change these numbers. So instead of balance, let's say have custom weights. So what do you mean by these custom weights? Like, since in the original data set, you see that the category 0 had like 23,000 rows, and category 1 had, like, say, 6,000 odd rows, right? So it's almost like 4 times the category 1. So to balance this, what we do is we give a weight of 4 to 4.5 to this category 1 and a weight of 1 to category 0, so that the output classes, they get balanced, right? All right. So let's do that. So let's run the code from this side, and then let's see the change in the values, change in the model evaluation.